this set of videos, we are going to introduce a new data type and two particular operations that come along with this data type that are very useful to us. So the data type we'll be introducing today is called the integer data type. It's a data type that is built into the Python programming language, and the acceptable values to be stored within the integer data type are whole numbers, numbers that don't have a decimal point. If we're talking about examples of specific types of this object, we call them ints for short. Now, it may seem superfluous for us to introduce the integer data type because, after all, a float can hold any number with a decimal point, and we could just store integers as floats with a decimal of 0.0. So this data type seems as though maybe it's redundant. However, there are two additional operations that we can define on integers that do not make sense for floating point values and are therefore not permissible for floats, but that we very frequently need in computer science. So most of the content within these videos will be focused on those two new operations. It should be said that all of the other operations that you have inside of Python for floating point values, addition, subtraction, multiplication, division, and exponentiation, which is that double asterisk, two of these in a row, those operations can all be performed on integer values. However, we have two new operations we may also perform only on integers called the mod operation that we execute with a percent sign, and something called integer division, which we execute with two division signs right in a row. Now we'll get into the details of these operations shortly, but as you may guess, one of these has something to do with division. And so if you're wondering where these two new operations fall within the rankings of this GEMS acronym that we introduced previously, because we're dealing with something akin to division here, these two operations have a tied precedence with regular multiplication and division. So they'll still be evaluated before addition and subtraction, but they would not be evaluated until after any grouping or exponents had been computed. I'd like to start out with some examples of the mod operation, because we actually use modular arithmetic all the time in everyday life. So if you had never heard of the mod operator before, I promise you've actually used it. You just didn't know that that's what you were doing. So you use the mod operation anytime you think about things like, what time will it be 27 hours from now? If September 19th is a Saturday, what day of the week will October 19th be? And there are interpretations in all sorts of other areas as well. If you're a musician, in particular, if you've ever played in an orchestra and ever had to endure numerous measures of rests, modular arithmetic comes up when orchestra players are counting how many rests they need to wait before their part in the music begins. So let's walk through those a little bit. So at least for the first two examples, why don't you pause and think about how you would answer these questions? Because I do not think that you would answer them in an entirely straightforward mathematical way. For example, if I were looking at the clock and it were 9 o'clock, I would not get out my fingers and count on 27 hours from 9 o'clock and say, yes, in 27 hours, it will be 36 o'clock. That's not what you do to answer the first question. Most likely, in answering the first question, you identified a 24-hour time period from now as being totally irrelevant. In other words, 24 hours from now, it will be exactly the same time as it is currently, 9 o'clock. There are then 3 more hours between 24 hours and 27 hours, and so truly, we can compute what time it will be from now by adding 3 hours to our 9 o'clock to get that it will be 12 o'clock. In a similar way, one way that we could figure out what day of the week October 19th would be is to take the 30 days between September 19th and October 19th and break up the 30 days into 28 days, which would be indistinguishable in terms of the number of days passing. So our 28 days corresponds to precisely 4 weeks in our calendar. We then need to travel 2 more days in order to have completed a full month of September, and 2 days from Saturday is going to be a Monday, and we could figure that out without starting at September 19th and then just counting 30 days on the calendar. It's much more efficient to break that 30 days into some number of weeks plus a few days left over. Last but not least, if you are a musician, what I've done is put a picture of some sheet music right here, and you can see that there are various parts for violins, violas, and other string instruments. And each one of these collections of 4 measures at a time is what is called a phrase. If you take a look at this instrument right here, you'll see that the instrument plays in the first phrase and then must rest the entire second phrase. This instrument then continues to rest for a good portion of the third phrase before coming in again to play. Now, if you were playing this instrument and you've played your part and then you need to rest for a while, you may not count out every single beat of every single measure to know precisely when you come in. You may, for example, ignore this whole phrase and then resume counting again when you've reached the third phrase. It's a much more efficient use of your time. So these are examples in life where we often use modular arithmetic, which is a throwing away of some good portion of computation and just associating a larger number with a much smaller number that is the only number of relevance for us. In our next videos, we'll see a precise definition of modular arithmetic, but these handful of examples give us a feel for why we need modular arithmetic and how it comes up in real life.